Okay, this is Chapter 5, a survey of other common functions. We've already looked at linear functions, we've looked at exponential functions, and we've looked at log functions. We're now going to be taking a look at a few other in Chapter 5. So Section 5.1, Logistics Functions. Okay, logistic growth model. This is actually what populations really do. So in real-life situations of population growth that involves living things like people, plants, animals, whatever, population grows exponentially for a short period of time, and then the growth starts to level off. It's still increasing, but the rate of increase is actually starting to decrease until it reaches what's called the carrying capacity of the land. Now, depending upon the situation, the carrying capacity can actually have other names. The carrying capacity depends upon food, water supply, temperature, and that type of other things. It can change if there's a severe drought or something like that. It also depends upon how long is the gestation period for the animal. Does it take a long time for them to start to reproduce? So the curve that models population growth for living organisms is called a logistic curve or logistic growth. Okay, so the actual curve is logistic growth, and the type of growth is logistic growth. So on the next slide, we have a graph of what logistic growth looks like. It looks kind of like that. It looks kind of like a funny shaped out S. So it's like for a short period of time you're growing exponentially, and then notice it's concave up until about here, and then it's concave down. So remember, the point where the concavity changes, that's the inflection point, and that is where you're going to have your greatest increase, and then you're going to start to decrease, and then it starts to level off until it almost looks like a horizontal line that you're kind of getting very, very close to the carrying capacity of the land. So again, it's always increasing, so it's always going uphill. Concave up for a period of time, concave down. Now, with the formula for the logistic growth, we actually have a way to find the exact value for where the inflection point occurs. So the discussion of logistic truths and all their glory is beyond the scope of our course. Instead, we're going to state certain facts about logistic growth and how to find them on our calculator. Now, of course, you're going to be responsible for knowing these facts. And of course, regression is going to be in going to be in stat and calc. So the logistic curve. So the general formula for logistic curve looks like this. N of t is equal to capital K over 1 plus b e to the negative RT. Now this e again is the second of ln on the calculator. And this is consistent with the letters used by our textbook. However, it is not consistent with the letters used by the calculator. Now, what do these letters stand for? K is the carrying capacity. R is the exponential growth rate as a decimal number. So 5% would be 0.05. B is a constant that depends on the initial value and the carrying capacity, which is related to what the actual organism itself is and the environment in which it lives. And of course, T is time. It can be measured in weeks, months, years, hours, depends upon what the organism is. And the reason the book is calling it capital N of T is N stands for number of individuals or number of organisms. Now, we have the following facts about logistic curves. Number 1, the inflection point occurs at t equals k over 2. Okay, so the inflection point is at t equals k over 2. Notice it's the carrying capacity divided by 2. Or another way of saying it, that's 1/2 of the carrying capacity. So that's the t value or the x value. To get the actual functional value, you would take that number and plug it into the function. So you evaluate n of k over 2 in order to get the actual population. B is equal to k over n of 0 minus 1. Remember, n of 0 is the initial population. So B is the carrying capacity divided by the initial population, and then subtract 1 from that. Because of that minus 1, B usually is a number that ends in a 9. Usually, but not always. Now, if b is greater than 0, which, by the way, it always is, if b is greater than 0, then the logistic function will increase if r is greater than 0, and it will decrease if r is less than 0. Now remember, in the formula for n of t, there's a minus sign in front of the r in the exponent. So notice if r is greater than 0, that means you see the minus sign, and if r is less than 0, you don't see the minus sign. Most of ours will actually have r greater than 0. Number 4, the relationship between the growth factor A and the growth rate R is A is equal to e to the R. So remember, R is the growth rate, and the growth factor will be e to the R. And number 4, logistic function and curves are also called Gompertz functions and curves, respectively, in honor of Benjamin Gompertz, though it's not really accurate. Gompertz curves are actually a little bit different than logistic growth curves, but they look an awful lot alike. Some examples. Okay, number 1, the population of people in Wassanet County infected with the Waterloo virus T days after the initial exposure to the virus is given by this. P of T is equal to 600 over 1 plus 299 e raised to negative 0.78 T. Here are the questions. Question A, what is the exponential growth rate? Part B, what is the daily percentage growth rate? Round your final answer to the nearest tenth of a percent. Question C, what is limiting value? Question D, what is the optimum infection level? Question E, graph the function, use an appropriate window. And question F, for how many days is the rate of increase increasing? Round to the nearest tenth of a day. Now, trying to set the appropriate window, we can actually get some of that by looking at what the function is, because remember, inside of here is the carrying capacity. Use kind of the maximum number. And also inside of here, we can figure out what the initial exposure was. But usually you can't have negative values. So kind of like our x min and y min would be 0 for part E. Okay, our solutions. Okay, comparing this function, the 601 plus 299 e to the negative 0.78 t to the standard one, k over 1 plus b to the negative rt, we're going to see that r is 0.78. So your exponential growth rate is 0.78. Part B, using a equal e to the r, we're going to get a is equal to e to the 0.78. That's the exact value. And so we, of course, would take out the calculator to figure that out. So we get about 2.18147. And to get it to the nearest percent, we're going to use r is equal to a minus 1. We had this from chapter 4. So r is going to be 2.18147 minus 1, which is going to be 1.18147. Now remember, that's the decimal number. To make a percent, just say times 100. And rounding to the nearest tenth, when we do times 100, the decimal point moves here, so it would be 118.1%. Remember, we did this relationship between A and R way back in chapter 4, the growth rate and the growth percent. Part C, limiting value is k is equal to 600, right? Remember, k is the limiting value. It's the numerator. Whatever number is in the numerator, that's your limiting value. For question D, the optimum infection level is the inflection point, so it's going to be k over 2, so 600 over 2. So at 300 people, that is the optimum infection level. That is when the rate of increase is at its greatest. Okay, part E was the graph. Okay, so since time of population cannot be negative, my x min and y min should not be 0, so I made them 0. The carrying capacity is 600, so I should have a y max slightly greater than 600. Okay, I went to 1,000. Okay, just kind of arbitrarily went to 1,000. So I've arbitrarily chosen 25 for the maximum x, so remember that's going to be 25 hours. So, and my x scale was 5. When I did that, this is what my graph looked like. Okay, so you can kind of see it's getting very close to that limiting value. So we've done enough graphing that I really didn't feel like I needed to do that separately on the calculator. Okay, in order for the rate to be increasing, we need to find where the graph is concave up. Remember, the inflection point we found in part D was 300. So we need to find the value of t when y is 300. So using the crossing graphs method, so here's our original function. Here is y2 being 300. The intersection point was 7.308, etc. So the rate of inflection is increasing for the first 7.3 days. And then notice after that, the rate of inflection starts to decrease. Question number 2. The population of catfish in Lake Doggone behaves according to the logistical model. Initially, in the year 2000, there were 200 catfish in the lake. The catfish population increases at a rate of 4.55% per year. In environmental conditions, limit the number of catfish in the lake to 1,200. Find the logistical model N of t that will give the population of catfish in the lake t years since the year 2000. If necessary, round all values to 3 places right at the decimal point. Use the model to estimate the population of catfish in the lake in the year 2016, rounded to the nearest whole number. Now, since these are populations, whenever we're looking for the functional value, we will either round to the nearest whole number, or when you're doing the homework problems in WebAssign, or on test even, read the directions carefully to say, do they say round to the nearest whole number, or do they say round down to the whole number? Now, in this one, we're going to round to the nearest whole number. Now, there really are 2 questions here. One, you find the model, and the second one, you're going to use the model to find out what happens in the year 2016. And notice that's 6 years after the year 2000. So let's see, our solution. Okay, we're given the carrying capacity is 1,200, right? The environmental conditions of the number of catfish in the lake, 1,200. So we know the value of K. K is 1,200. Now we're going to use it to find B. So we're going to use the carrying capacity in order to find B. Okay, remember, B is equal to capital K over N of 0 minus 1. Remember, N of 0 is the initial amount. Okay, now we got the carrying capacity. We got K is 1,200. Okay, now do we know N of 0? It says in the year 2000, there were 200 catfish. So we know N of 0 is 200. So B is going to be 1,200 over 200 minus 1. See, 1,200 over 200, we get 6 minus 1, which is 5. So B is 5. So we know the value of K. We know the value of B. The other value we need, we have to find R. We got K, we got B, now we're going to find R. So we're told the population grows at a rate of 4.55% per year. So A is 100% plus 4.55%. Remember, this is from chapter 4 because we got growth. It's 1 plus the R. So 104.55%. Which has a decimal number, 1.0455. Now, since A is equal to e to the r, okay, one of our properties of the log says that the natural log of A is equal to r. Remember, when we had 10 to the t was a number, we took log. Now, since we have e, we're doing ln. So the natural log of A is going to be r. So the natural log of 1.0455 is going to be our r. So we get about 0.044 when we round it to 3 places. So we know K, B, and R now. So our N of t is 1200 over 1 plus 5 times e to the negative 0.44 t power. Now, we're supposed to use that to find out what happened to the year 2016. So let's go ahead and take out our calculator anyway and figure this out. So let me move this over here. So for 2016, t is going to be 6. It's going to have 1200. Now, because I'm only making one calculation, that's the reason I'm not putting in through y1. Divided by, open parenthesis, 1 plus 5 second ln negative 0.44, whoops, needed a 0 there, negative 0.044 times 6. Because remember, 2016 is 6 years after, whoops, I don't need that parenthesis there, 6 years after when we began doing this, which was the year 2000. So I get this value, 247.94, so the nearest whole number, 248. So again, in the year 2016, t is 16. Ooh, I had the wrong value, 16 instead of 6. So let me see if I can fix that. So let me edit this, second, enter, and go back and change my 16, or excuse me, my 6 to a 16. So 1, 6, and now let's enter. So 345.52, so the nearest whole number, 346. So we do that calculation, and we get 346 to the nearest whole number. Okay, logistic regression. Now remember, in this one, this previous one, there was no data given. There was just information that allowed us to find the K, the B, and the R. So we couldn't use the calculator to get the regression model. So logistic regression. So we're going to look at using our calculator to find logistic curves. Now again, the process is what we've done before. Logistic is actually in the stat count thing. It'll actually say logistic. So again, just to see it here, let's take out the calculator here. So let me also clear this out since I'm going to be doing stuff. So if I do stat calc, we look for logistic. And notice it's choice B. So if you do alpha B, you can go straight to it. So we don't really have a test to determine if logistic model is best. We don't. There's no process we can do with the data other than maybe plot it and see if it looks like an S, or if we're specifically told that the population is growing according to a logistic model. So some examples. Number one says, find logistic growth model N of T that models the following data. If needed, round all values to 3 places right at the decimal point. Remember, those values we find are called the parameters. So then graph the model and the data values using an appropriate viewing window. Okay, looking at our values of t, which is going to be x, 0 to 24, and are the increments of 4? Yeah. So I would use my x max to be 28. You know, what would be the next value, and my scale would be 4. And for the y values, 0 up to, okay, since the 170, I don't know, 200 might be good for a max when I draw the graph. So, our solution. So step 1, we're going to enter t values into L1 and the ft values into L2 using stat and edit. Okay, let me go ahead and do this then. So, take out the calculator, stat, it's already on, edit, enter. Okay, the L1s, 0, 4, 8, 12, 16, 20, 24. Okay, you got all the x values. Okay, now for the L2s. Okay, 2, 6, 18, 48, 90, 150, 170. Okay, and again, make sure you didn't skip anybody and make sure they're all right. And then, of course, we're going to have to quit that, so quit. So let me get caught up here. So there are my values. Again, be sure they're correct. Be sure everything lines up like it's supposed to. Okay, step 2, we're going to quit the screen and do logistic regression where it's choice B. So if we enter, we're going to get this screen. And since we're going to graph, I'm going to store it. Now, in order to make sure everything does like it's supposed to, let me set my float here. So mode, float, we're going to 3 places, so float on over to 3. Remember, I didn't do this on the calculator on the slide. If I quit this, so let's see, stat, calc, it's choice B, so alpha B. Okay, my L1 and L2 are fine. I want to store this into Y1 bars, Y bars, function, enter, and then we calculate. It actually takes a little bit longer to think about the logistic growth model for some reason. Okay, and remember, it's using these letters C, A, and B like that. So we got our A is 101.934, our B is 0.290, our C is 189.185. Okay, so remember, his C is what we call K, his A is what we call B, and his B is what we call R. Okay, so we do all that. So we're going to, again, this is putting the Y1 to store the regression model, okay, and then to calculate. So now again, this one I didn't set my float to 3. So our NFT is 189.185 over 1 plus 101.934 e to the negative 2.90t. Okay, now when I plot this, I got to turn on a stat plot, so let me quit this, quit. Second stat plot, let's turn on number 1, turn it on, and let's see my windows. Okay, minimum 0, okay, the X max, see, I said I was going to go out to, let me go with my data again, go out to 28 in increments of 4, so 28, the scale will be 4, minimum of 0, and since we had a maximum of that 170, let's go out to 200, and let's do it in increments of 20, why not? So, graph. So the model does a fairly good job with the data. And again, here's my window. 0.284 by 0.220. And again, I turned on stat plot 1. And it gave me that, which again is pretty doggone good. Example number 2. A company introduced a new software product in a city. The company advertised their product on television and found the following data regarding the percent P of people who bought the product after X ads were run. Now notice, since P is percent, the most it can be is 100%. So it's kind of like the problem itself implies a carrying capacity. So my X values were in increments of 10, 0, 10, 20, 30, 40, 50, 60. Remember, this is the number of ads that were run. And here's the percent of people that bought the product. Okay, so part A, find logistic model n of x, because I used x instead of t. That model is above data. If necessary, round values 3 place, right at the decimal point. Question B, based on model, at what level, okay, the number of ads placed was the rate at which people were buying the software the greatest, round to the nearest whole number. Based on the model, estimate the percentage of people that will buy the software if 100 ads are run, round to the nearest tenth of a percent. And in question D, graph the model and data using the appropriate viewing window. Well, again, looking at our values, our viewing window for X max should probably go to 70, one more place in increments of 10. The P, remember, these are percents, so 100% is the most you're ever going to see. So it's kind of like a min of 0 and a max of 100. So let me get our calculator set up here. So let me quit this. Let me clear out my y equals. Quit. Let me clear out my lists. Choice 4, clear all the lists. There we go. Okay, now we're still rounding to 3 decimal places, so I'm going to leave my float, my mode float, I'll keep it at 3. So set and quit. So see, to get caught up now. Okay, so our solutions. Okay, we're going to enter the data into the calculator, so let's go ahead and do that, entering the data into the calculator. So whoops, I guess I should go back to the data, huh? So stat, edit. Okay, the L1, 0, 10, 20, 30, 40, 50, 60. Okay, then scroll over to get the y's. Okay, I believe that was 0.2, yes. So 0.2, 0.7, 2.7, 9.2, 27, 57.6, 83.3. Okay, and of course we quit. Okay, now let me get caught up here. So I've got my data in, and then we're going to store the model into Y1. So again, let me get caught up here. Now, because in this one I didn't round, and in the previous, and in this calculator I'm rounding, the values are going to be already rounded for me. So stat calc. Remember, it's choice B, alpha B. L1 is fine, L2 is fine. My frequency list, always leave it blank. Stored in vars, y vars, function, enter, and let's calculate. And there it is. So again, these are already rounded off for me. So my growth model, n of x is 100.075 over 1 plus 487.438 e to the negative 0.130x. Remember, we're using x instead of t. Okay, and question B was, at what level was the rate at which people buying the product the greatest? And we're going to round to the nearest whole number. So remember, we need to find k over 2. Okay, k over 2. So it's going to be 100.075 divided by 2. So when you do that number crunching, to the nearest whole number, 50 adds. Okay, so it's greatest when you have 50 adds. Question C. You need to find n of 100. Because we know the percentage of 100 adds are run. So if we do this on calculator here, now again, because I did the rounding on this calculator, so vars, y vars, function, y1 of 100, what's this? 99.965. Notice to the nearest whole number, that would be 100. Let's see what happens here. Okay, so the nearest tenth of a percent, that's 100%. Okay. See, would I get the same thing if I rounded the nearest tenth of a percent here? Yeah, because that's going to go it up. Yep. So 100%. Notice I reached the carrying capacity right there. And in question D, okay, the window. Okay, so I set my window to match. Window, because again, you can't have a negative percent. Okay, I went up to 100, make it match, in increments of, whoops, another 0, in increments of 10, and the y min 0, and for the y max, since these are percentages, the biggest it can ever be is 100%, and in increments of 10 as well. And my stat plot 1 is already turned on, so graph. So again, it does a fairly good job of modeling the data. That's the end of section 5.1.